Gibbs free energy. What is Gibbs free energy? It is the portion of a system's energy that is available to do work. This concept combines enthalpy and entropy. Gibbs free energy is used to predict the direction of a chemical reaction under two conditions: constant temperature and constant pressure. Equation and units. The Gibbs free energy equation. Considering that Gibbs free energy measures the spontaneity of the process, the Gibbs free energy change for a given process at constant temperature and pressure is delta G is equal to delta H minus T delta S. So here the H represents the change in enthalpy of a reaction, the T represents temperature in Kelvin, S represents change in entropy, and then delta G represents change in the Gibbs free energy. So we have Gibbs free energy at a standard state. The equation is the same, except that we have to look for three criteria. One is that the temperature has to be 298 Kelvin, the pressure has to be 1 bar, and the concentration has to be 1 mole. Next, we have Gibbs free energy and equilibrium. So at equilibrium, the forward and reverse reaction proceed at equal rates. Also, the driving forces in each direction is equal because the free energy of the reactants and products under equilibrium condition is equal to delta G is equal to 0. We also know that at equilibrium, Q is equal to K. So we have delta G naught is equal to negative RT ln K. Here in this new equation, we have the R that represents the universal constant and K is an equilibrium constant. And then we have Q, which is the reaction quotient. So this equation allows us to convert between delta G and the equilibrium constant. Here's a table that shows the relationship between K and G. If K is less than 1, delta G is positive and the reactants are favored over products at equilibrium. And then if we have K that is greater than 1, delta G is negative and the products are favored over reactants at equilibrium. So how do we find the delta G for a reaction? We have the sum of standard free energy of formation of products minus sum of standard free energy of formation of reactants.
Now I'm going to talk about endergonic and exergonic reactions and how they relate to delta G. To begin understanding these reactions, we can look at their prefix. Exergonic is similar to exothermic in that something is being released. However, the difference is what is being released. For exothermic, heat is being released, and for exergonic, free energy is released. The release of free energy is associated with a negative Gibbs free energy as the products contain less free energy than the reactants. The sum of the standard free energies of formation for the reactants will be less than that of the products. If we move on to endergonic reactions, we can again look at the prefix. Endergonic is similar to endothermic in that something is being absorbed, with the difference again being what is absorbed. For endothermic, heat is being absorbed, and for endergonic, free energy is absorbed. For these reactions to proceed, reactions must gain free energy from their surroundings. This absorption of free energy is associated with the positive Gibbs free energy as the products contain more free energy than the reactants.
In thermodynamics, a spontaneous process means that once the reaction starts, it will continue to occur until there's an external input of energy. In other words, it takes place on its own, naturally, under a given set of conditions. A good example of this is a system of water on Earth, acting under the influence of gravity. Water flows spontaneously downhill, and the direction of flow is from a position of greater potential energy to one lesser potential energy. This is known as exergonic reaction, an energy-releasing reaction. And in terms of phase change, ice melting at standard condition or water freezing under the freezing point are also included as a spontaneous reaction. And note that the sign of delta G is always negative for spontaneous reactions. Now, for non-spontaneous processes, the change in Gibbs free energy is always positive. In other words, delta G has to be greater than 0. And unlike spontaneous, a non-spontaneous process is a process that cannot take place by itself, so it requires a continuous external input of energy. An easy example would be pushing a bicycle uphill, or how water cannot freeze at room temperature, or how ice cannot melt at negative 10 degrees Celsius. All of these things require a little bit of energy, so it's an endergonic reaction, where reactants are favored. Also, one important thing to note is to not confuse the spontaneity of a reaction with the speed at which it occurs. The two things are unrelated, and the rate of a reaction is related to kinetics. Now, how can you tell if a reaction is spontaneous or not? Well, the answer lies in this equation. As all of you should know by now, this equation is to calculate the Gibbs free energy of a reaction. And know that Gibbs free energy is a really good indicator of if we have a spontaneous or a non-spontaneous reaction. Remember that if delta G is negative, it's spontaneous, and if it's positive, then it's not spontaneous. And there are 4 cases to this. The first 2 are very simple. The first case is where the sign of delta H is negative and the sign of delta S is positive. So when the change in enthalpy is negative and the change in entropy is positive, then delta G is always going to be negative. It doesn't matter what the value of entropy or enthalpy you have, all that matters here is the 2 signs that are agreeing to each other. Because remember that if delta H is negative, then it means that it's an exothermic reaction, so we know that the heat is lost by the system but gained by the surrounding. While positive delta S increases in entropy, and it matches the definition from earlier, so we know that it's a spontaneous in the forward direction. And what's nice about this is that we automatically know that the opposite of this will be non-spontaneous. So in a situation where delta H is positive, which is an endothermic reaction, so there's an increase in enthalpy, and negative delta S, so entropy decreases during the reaction, this means that the free energy is always going to be positive. It doesn't matter what the temperature we run the reaction at, the reaction will always be non-spontaneous in a forward direction, but spontaneous in a reverse direction.
We are now going to talk about some cases where the sign of delta G is dependent on temperature. In these cases, the signs of delta H and delta S will be the same. For exothermic reactions in which delta H is greater than 0 and the reaction is accompanied by an increase in entropy, a positive delta S, the reaction will be only spontaneous at high temperatures. Looking at the equation, we can see this would give us a positive number minus another positive number. Delta G would only be negative if the second number, which would be equal to T multiplied by delta S, would be greater than the first number, which would just be delta H. For this to happen, delta S needs to be accompanied by a higher temperature so that it outweighs the delta H. If the temperature is small, delta G will be positive like the image shows. Now if a reaction is exothermic, which delta H is less than 0, and it is accompanied by a decrease in entropy, a negative delta S, the reaction will only be spontaneous at low temperatures. Looking at the equation, we could see this would give us a negative number minus another negative number. However, we know that if we subtract a negative from a negative, it becomes a positive. Delta G would only be negative if the second number, again, T multiplied by delta S, had an absolute value that is less than the first number, delta H. For this to happen, delta S needs to be accompanied by a lower temperature. If the temperature is high, delta G will be positive like the image shows.
So for summary, just note that when the sign of delta H and delta S are different, then it's not temperature dependent. So it's going to be either spontaneous at all temperature or non-spontaneous at all temperature. And the sign of delta H and delta S are the same, then it's going to be temperature dependent and it becomes a little bit complicated. But all you got to remember is that increase in entropy is a spontaneous as long as we have a high enough temperature. And likewise, if we have a decrease in enthalpy, so that's an exothermic reaction, and decrease in entropy, that's going to be spontaneous but only at low temperatures.
Now that we have learned about Gibbs free energy, let's answer a few questions. So what are the factors that affect Gibbs free energy? It's entropy, enthalpy, and temperature. Which of the following changes in the thermodynamic property would you expect to find for the reaction Br2 gas to 2Br gas at all temperatures? The correct answer is B. Why is that? So the product side has more moles compared to the reactants, so the product side has more entropy. True or false? When both entropy and enthalpy are positive, the reaction is spontaneous at higher temperatures. The correct answer is true. Gibbs free energy predicts how fast or slow a reaction is. True or false? Correct answer is false.
Next, we have two word problems. So this is the first one. Calculate the standard free energy change for the formation of nitrogen dioxide from nitrogen and oxygen at 298 Kelvin. Okay, so to find our delta G naught, we can use the equation. So we know our values over here, and we can just plug it into the equation. For delta S naught, we have to convert that to kilojoules. So we have, then let's plug that into our equation. So using my calculator, I get the answer. So is this reaction spontaneous or non-spontaneous? So since delta G naught is positive, we have a non-spontaneous reaction. Our last question, the reaction of calcium carbonate to produce calcium monoxide and carbon dioxide has an equilibrium constant at 25 degrees Celsius of 2 times 10 raised to the negative 23. What is the delta G naught for this reaction? So to find the delta G naught, we can use the equation. So we have our temperature at 25 degrees and we have the equilibrium constant. So let's just plug it into the equation. And the temperature, we know that it is 298 K. Using my calculator, I get the answer. Then let's just convert that to kilojoules. So we have, and that's our delta G naught.